let's see. So last time I handed out notes on the application that Zyberg wouldn't do. I'm not sure everybody got them. And here's a new set of notes. Okay, so let's remember what we were discussing last time. We were discussing gauge theory with a finite group. The point being that if I have a principal gamma bundle, that's also the same thing as a principal gamma bundle with connection. So we're going to discuss connections in general a couple lectures down the road. But what I'm going to say about gauge theory for a finite group applies to gauge theory for any compact group if you simply make the replacement principal gamma bundle by principal G bundle by principal G bundle in connection. Okay. So you remember that we're thinking of a field theory as some kind of functor from a geometric category to a linear category of vector spaces and maps between those. So to a space Y, we associate a Hilbert space, H of Y, to a Bordism from Y in to Y out, with some space-time X, we associate a transition amplitude from H of Y in to H of Y out. And now we can give that category different kinds of extra data. We could talk about manifolds equipped with metric, manifolds equipped with conformal structure, spin structure, all sorts of things, to get different kinds of geometric categories appropriate for different field theories. Now, recall that G is a global symmetry of my field theory if, first of all the spaces H of Y are G representations. And secondly, the transition amplitudes of H of Y in to H of Y out commute with the G action. In other words, the transition amplitudes are G intertwiners. Okay. Now I was asked last time, what about Lorentz symmetries and Poincaré symmetries? And those are not global symmetries in the sense that I'm discussing. You see, if you want to take into account Lorentz and Poincaré symmetries or conformal symmetries, what you would do is that you would endow the geometric category as, say, manifolds with metric. And then in the morphisms of this category, you would include morphisms between, let's say, Y1G1 and Y2G2, which are diffeomorphisms from Y1 to Y2, such that the pullback of the metric G2 is G1. So then you see the automorphisms are the isometries. So you have a manifold with a metric on it, like a Lorentz metric on a Minkowskian space-time. The automorphisms would be the isometries, like the Poincaré group. And those would act on your Hilbert space because you have a functor. Okay? Now, but notice, of course, that those depend on your choices of x and y. Right? Here we have all manifolds with metrics on them. Okay? So, you know, the automorphism group, in that sense, depends on x and y. Here I'm choosing a G where I have G representations for all y and G intertwiners for all x. Okay. So that's a better answer than the one I gave last time to why we're not thinking of G as something like Lorentz or Poincaré. We're thinking of G as an internal symmetry. Okay. Now, in this situation, when we have a global symmetry in this sense, we can gauge the G symmetry, as we discussed last time. And as I said, that consists of two steps. Step one is form A, this is a choice, G equivariant theory. So let's call it curly F equivariant. In step two, we sum over G bundles with connection. Now, of course, each of these steps needs a good deal of explication. And last time I described step one. Let me just summarize it very briefly. So in step one, what we do is we enhance the category. Let's say our geometric category, I think I call it S, or spaces. We enhance S to S of G, which is equal to spaces with principal, and let's do the case of a finite group, with principal gamma bundle. So that means that the initial spaces are now principal gamma bundles over Y, and the morphisms are principal gamma bundles over organisms X. And so now what we want is a functor, F equivariant, again goes from S of gamma to vector spaces. So that means that if I have a principal gamma bundle over my in or out spaces, I have a Hilbert space, let's call it H equivariant. And if I have a principal gamma bundle over a Bornism, space-time, then I have an F equivariant, which maps from, let's say, P naught over Y naught, H equivariant, to H equivariant, P1 over Y1. And then there's compatibility with the, we have to have some sense in which we're actually gauging the original global symmetry. So, you see, to every Y or X, there's a canonical G bundle or gamma bundle, namely the trivial gamma bundle. And so we require that H equivariant of Y times gamma is the old H of Y, and F equivariant of X times gamma is the old F. And then there's some further conditions that I'm not going to go through in detail again because we discussed that last time. Now we also gave an example of this rather abstract setting. I remind you that we had the example of a nonlinear sigma model where the nonlinear sigma model, which was based on maps from x or y into M. And if M had an isometry, then an isometry group gamma, then we had a global symmetry. That field theory has a global symmetry. We can gauge it. And we extend the fields, in this case, to equivariant maps. So we would now choose a principal gamma bundle over x or y, same thing for both, and then we would have phi tilde from P into M, which commutes with the G action on M and P. Now, in particular, if P is equal to x times gamma, an equivariant map, phi tilde, to M is the same as an ordinary map phi from x into M. You see, because phi tilde of x comma gamma is just going to be equal to phi tilde of x comma 1 dot gamma. So all you have to know is phi tilde of x1. But in general, all we can say when we have an equivariant map from P into M, all we have is a map straight phi from x into the quotient space. Okay, when you have an equivariant map like that, you get a map from x into the quotient space. So the idea is that you take P as a principal bundle over x. You take some x here, you choose some lift over here, you map it over here, and then you take its equivalence class, and then that's well defined. Okay. Now, we then specialized to the case of 1 plus 1 dimensions. Okay? And there, remember that we looked at the groupoid of principal gamma bundles over the circle. So let me remind you about that. That groupoid is the same as the groupoid, what I call gamma / gamma, where gamma acts on itself by conjugation. So recall how that goes. So for all group elements, gamma and gamma, we can define a principal gamma bundle by taking R times gamma divided by Z, where the equivalence relation here identifies S plus 1 gamma prime with S gamma prime. So the idea is that this S, so we're projecting here to the circle by taking the equivalence class of little s and gamma goes to e to the 2 pi I s in S1. Okay, so the idea in this gluing is that as I go around the circle, I have a holonomy, a monodromy associated with this discrete cover, which is given by gamma. So upstairs, I have these two guys glued together by gamma. And that's the gamma in the piece of gamma here. So I remind you that it suffices to look at these bundles. And then at the very end, we showed that p sub gamma 1 is isomorphic to p sub gamma 2 if and only if gamma 2 is equal to gamma naught, gamma 1, gamma naught inverse, or some gamma naught. So if these holonomies are conjugate, then we wrote an explicit bundle isomorphism, and in particular the automorphisms of a bundle p sub gamma is the centralizer group of that gamma. So we had a picture then of the space. So we had a picture of the space of principal gamma bundles over S1, okay, which I'll draw again for the case. So for example, for gamma equals S3, okay, so for every group element, we have a point. So let me draw them like this. So the points in S3 are 1, 1, 3, 1, 2, 2, 3. And then we have the cycles, 1, 2, 3, 1, 3, 2. And then we're looking at the group acting on itself by conjugacy. So we have 6 elements taking 1 to 1. The things here that are invariant under conjugacy are just the cyclic group generated by each of the transpositions. And then we have the other elements conjugating one transposition into another. In this case, the cycles are take a cycle into a cycle, because that's a cyclic group. That's the origin of the name. And so we have that for the action of the conjugation by the cycles, and then conjugation by the transpositions takes 1, 2, 3 into 1, 3, 2. Okay. So that's what your groupoid of principal gamma bundles looks like on the circle. Looks like for S3. Oops, that's S sub 3. I think you all understood that. And then just to review, the last thing I did was say, what does, in this particular case of a nonlinear sigma model, in 1 plus 1 dimensions, if we put these two things together, what is an equivariant map, phi twiddle, from p sub gamma into M? What does that look like? There's a... Yeah, okay. So what does that look like? Well, then I argued that, okay, if I have an equivariant map, a gamma equivariant map into M, well, I can pull back up to R times gamma here, and instead talk about this map, phi hat. And then, remember, phi hat satisfied two equations. First of all, I want it to descend to a map from P gamma into M. And so I'm trying to impose this equivalence relation on my function. So I have phi hat of S comma gamma gamma prime. So that's, if you like, the descent step. And then there's the equivariance condition that says that phi hat of S comma gamma prime gamma double prime is phi hat of S comma gamma prime gamma double prime. On the other hand, as I just said, to give an equivariant function on the principal bundle is the same as to give just a function, so we could let phi check of S be phi upper hat of S comma 1. And we capture all the information of phi hat, and therefore phi tilde, by just looking at phi check of S, and then we did a little calculation, which I won't repeat, to show that phi check of S plus 1 is phi check of S times gamma. Okay? So we had the gamma twisted boundary conditions. So we conclude, and conversely, if I've got such a twisted function, conversely, given such a phi check, we can define an equivariant map phi twiddle from P gamma into M. Okay? So the space of equivariant maps into M is the same thing as the space of twisted functions in this sense. And the intuition is that if you have some kind of orbifold, like a cone where you took R2 mod some discrete group, you can have some closed string on this cone which lifts to R2 to a string like this. Okay, and the covering space, the lift of this picture is this picture. And so these are what the twisted states, or how the twisted states are to be pictured. So you notice a few things about this. First of all, they tend to be massive. If you try and take them away from fixed points, you see they stretch, and strings have energy per unit length. And so then these states tend to be concentrated near the fixed points. Okay. In any case, what we get here, this space of equivariant functions, if we look at wave functionals of them, then we have H equivariant of these principal bundles, P sub gamma, and these are called, in orbifold theory, twisted sectors. Okay, so that's a long summary of what we said last time. Are there any questions about that? So we completed step 1. And now I want to talk about step 2. Namely, summing over principal gamma bundles with connection. Okay. Okay, so the way I'm going to approach this is let's begin by thinking about the partition function. So recall that if I have a closed manifold, okay, if X is a closed manifold, so the boundary of X is the empty set, then it's a cobordism of the empty set to the empty set. So by abstract nonsense, my topological field theory must associate to that a complex number, Z of X, called the partition function. So what should our Z of X in our gauged theory be? Well, the first idea is that we just sum Z of the equivariant theory over all P, where we sum over all principal gamma bundles over X. Okay? But there's obviously something wrong with this. Anybody want to venture to say what's wrong? So I'm trying to define the second step. I've told you what it means to have an equivariant theory. Okay? Which is coupling, defining a coupling of that theory to external gauge fields, if you like. Yeah?
Some of the principal bundles are related by automorphisms. So
Isomorphisms.
Yes.
Yeah, right. Absolutely. So remember, the principal gamma bundles form a groupoid, and if P is isomorphic to Q, if you have a P here and a Q here, there's an isomorphism between them, then this just follows from the axioms of the equivariant theory. Z equivariant of P is equal to Z equivariant of Q. And if they're isomorphic, then clearly we're overcounting. Okay? So we want to divide, in some sense, by isomorphisms. Okay? Now, if we divide by isomorphisms, then what we're doing is we're summing over isomorphism classes of bundles. So instead of summing over 6 points here, we'd be summing over 3 islands, connected components. Okay? But now let's remember that some bundles have automorphisms. So if we're dividing by self-identifications, we should divide by the order of the automorphism group. So this is not quite the right definition. The right definition would have Z gauged equals the sum over P in the isomorphism classes of the principal gamma bundles on X of 1 over the automorphism group of P times Z equivariant P. And that is a correct definition. Now, I did something a little funny here. You could ask me, what is P? So I'm summing over the isomorphism classes. But for each isomorphism class, I made a choice of principal bundle. So Omar asked me last time, what is gauge fixing in this story? And that's where gauge fixing comes in. So what I've done is that for each isomorphism class, I've made a choice in order to evaluate this contribution. I made an actual choice of a principal gamma bundle. Now, because of this property here, it doesn't matter which choice. That's the invariance of the physical answer under different choices of gauge. Okay? So what gauge fixing is making a choice of a principal gamma bundle with connection, a unique choice for each isomorphism class of such. Okay. So this division by the automorphism group here is the analog of what you read in field theory textbooks, in Yang-Mills theory, where we divide by the volume of the group of gauge transformations when we're summing e to the minus Yang-Mills action when we do the path integral in a Yang-Mills theory. This is a precise version of that, absolutely rigorously defined for the case of a finite, albeit for the case of a finite group. What about the Hilbert space? What about the Hilbert space? Well, it's the same idea with the Hilbert space. So again, we need to integrate over gauge fields. So that means in order to define our Hilbert space, H gauged on some spatial slice Y, we have a good notion of summing of vector spaces. So your first idea is to sum over principal gamma bundles P over Y of H equivariant of P over Y. But again, we have the same problem here. We've overcounted. Okay. So how does this looks a little different now in the Hilbert space case. So you see, if we have a P over Y and a Q over Y, and we have some bundle isomorphism alpha, so alpha is a bundle isomorphism, then you see the analog of this equation, which is unfortunately not visible, but now it is. The analog of this equation is that in the equivariant theory, there's an isomorphism of the equivariant Hilbert spaces. And that's an isomorphism of Hilbert spaces. So we're talking about wave functions here. So we want some kind of wave functions of P over Y which satisfies this kind of equivariance. Namely, we want alpha tilde of psi of P over Y to be psi of Q over Y. And this is known as the Gauss law. The Gauss law says that physical wave functions should be invariant under gauge transformations. So to correct this formula here now, what we do is we sum over P in the isomorphism classes of principal gamma bundles over Y. And what's the analog of dividing by automorphisms? Well, each bundle has an automorphism group. Because of the properties of the equivariant theory, that automorphism group acts linearly on the equivariant Hilbert space, and we should take the invariant states. That's part of what it says, what the Gauss laws say. So this means take the invariant states. Okay, so this is the definition of the Hilbert space of the gauged theory. So again, you have two steps. You have a global G-symmetry. You then gauge it in two steps by first specifying a coupling to the external gauge fields by making an equivariant theory. That's a choice. And then you sum in this way over theory over gauge bundles with connection. Okay, and that's a gauge theory. Okay. Now, yeah.
If one wanted to practically, in practice, find these gauge invariant states, I mean, for the case of a finite bundle of discrete group,
Yeah.
we would be able to do that explicitly. Is there
Right.
some kind of like BRST analog that would let us do it in cases where
Well,
it's
the
not easy to
most
do manually?
naive thing to do is to average over the group of gauge transformations. Now that's a functional integral in general, and so it's subject to all the difficulties of having a functional integral. All right, so now I want to go back to 1 + 1 dimensions and show you that all of this is reasonable by, let's check, by checking a basic fact. Namely, the gauged partition function on y times a circle should be equal to the trace over the gauged Hilbert space of e to the minus beta times the Hamiltonian, where beta is the length of the Euclidean time circle. So this is the standard story that if you have a space and you cross it with a Euclidean thermal circle, okay, then the partition function on the theory y times s1 should be the trace over the Hilbert space where you propagate in Euclidean time and then glue together. Okay, is everybody with that? You know that? Okay. So now I want to check this for 1 plus 1 dimensions. It's really a beautiful check, so let's do that. And maybe it will help you understand a little better why these are good definitions. All right. So in 1 plus 1 dimensions then, we're trying to check z gauged. So we're putting y equals s1. So we're looking at z gauged of s1 times s1, in other words, the 2 torus, is equal to the trace of h gauged of s1 of e to the minus beta times the Hamiltonian. Okay, so what's h gauged in this case of s1? Well, that's a sum, by what I said before, over gamma in the conjugacy classes of capital gamma of H equivariant of those bundles P gamma I defined before, and remember their automorphism group was the centralizer of the group element gamma. Okay? So that's writing out this rather abstract statement in this particular case of 1 dimensions. Any question about that? Right. Okay. So the trace over h gauged of S1 of e to the minus beta h is then the sum over these. But now, because of equivariance, I can simply write the sum over all the group elements. If I remember to divide by the overcounting, where I divide by the order of the conjugacy class of gamma, of trace h equivariant of p sub gamma invariant by z gamma e to the minus beta h. Okay, is there any question about that? Is it clear what I did? C of gamma is the order of the conjugacy class of gammas. Okay, so here, if you like, I was again doing this kind of gauge fixing, making a specific choice for each isomorphism class. And here, I'm simply summing over all of the bundles with connection, and then explicitly dividing by the overcounting factor, which is the kind of thing you see in this formal expression here. You sum over all bundles with connection, and then you divide by the overcounting. All right. Now, how do we deal with this crazy thing here? Well, we introduce a projection operator. So there's a projection operator. We could write 1 over z of gamma 1, let's call it pi sub gamma 1, is 1 over z of gamma 1, the sum over gamma 2 in z of gamma 1 of gamma 2. Okay? That projects onto states which are invariant under this action of z of gamma. Let's call this gamma 1 here. Okay, so then inserting our projection operator, we now have the sum over gamma 1 in capital gamma, 1 over the order of the conjugacy class, the sum over gamma 2 in the centralizer of gamma 1, 1 over the order, sorry, that's the order of z of gamma 1 of the trace in h equivariant of p of gamma 1 of gamma 2 e to the minus beta h. Are there any questions about that? Okay. Now, this we can do something with. I think I can erase this. In the equivariant theory, we have to understand what's the meaning of this here. So what are we doing here? We're taking a circle where our gamma bundle over the space has holonomy as I go around gamma 1. And then we're propagating it in Euclidean time from 0 to beta. And then the trace is gluing back together, but with a twist by gamma 2. We're having gamma 2 act on the states before we glue back together, right? So what is that? That is equal to a torus where we have holonomies gamma 1 and gamma 2 over the torus. So you see, just the way we had these bundles p gamma over the circle, we have p gamma 1 gamma 2 equals R2 cross over z plus z of gamma, which is a bundle over the torus, where we now identify s comma t, let's see, s plus 1 comma t comma gamma prime is identified with s comma t gamma 1 gamma prime. So that says that I have holonomy gamma 1 around the space direction, the s direction, and s comma t plus 1 gamma prime is identified with s comma t comma gamma 2 gamma prime. That says I have holonomy gamma 2 as I go around the Euclidean time direction. Okay, so let's call this so the equivariant theory, right? The equivariant theory gives us a partition function for any bundle over closed manifold. So in the equivariant theory, Z equivariant of p sub gamma 1 gamma 2 over the torus is equal to trace of H equivariant of p of gamma 1 of gamma 2 e to the minus beta h. That's what I've just argued by these things here. And this follows from the formal properties of the equivariant theory. Are there any questions about that? Is it clear? All right, well, great. So now, let's just write this then as the sum over gamma 1 and gamma, the sum over gamma 2 in z of gamma 1 of 1 over the order of the conjugacy class of z of gamma 1, of gamma 1, and the order of the centralizer of gamma 1, and z equivariant of p sub gamma 1 gamma 2. Okay. But now, a little bit of group theory. Okay, so I'm going to continue this identity. Let's continue it up here. I claim that this is equal to the sum over gamma 1 in gamma, the sum over gamma 2 in z of gamma 1, of 1 over the order of gamma, z equivariant of p of gamma 1 gamma 2. Now why is that? Let me just justify that in one second. And so I can rewrite this as 1 over gamma of the sum over all pairs, gamma 1 and gamma 2, whose group commutator is 1. In other words, all commuting pairs of gamma 1, gamma 2, of z equivariant P of gamma 1, gamma 2. And now by the same kind of, I think I'm going to leave this as an exercise, by the same kind of considerations we've gone over several times, this is a sum over the principal gamma bundles on the torus of 1 over the automorphism, so we get P of gamma 1, gamma 2 if you like, of 1 over the automorphism group of P of gamma 1, gamma 2 of Z equivariant of P of gamma 1, gamma 2. Okay? So that, finally, is Z gauged of the torus. And so I've started with the trace over H gauged on the circle, e to the minus beta H, and I've ended with Z gauged of the torus. And that's precisely the check I wanted to make right here. Okay? So this last step here is easy. I'm leaving it to you as an exercise. So the only thing I have to justify still is why the product of this conjugacy class times this centralizer is gamma. Okay, but that's just standard group theory. So so you look at gamma acting on the conjugacy class of gamma 1 by conjugation. Okay, that's a transitive action, trivially. Okay, and what is the stabilizer of gamma 1? So you see, gamma is the action. If gamma prime is in here, the gamma action takes gamma prime, goes to gamma, gamma prime, gamma inverse. Okay? So that clearly takes any one point in the conjugacy class to any other. And what's the stabilizer of gamma 1?
Gamma 1.
Well, that's certainly in the stabilizer. It's true that...
Oh, sorry, the conjugate.
Sorry, this is... yeah. What's the stabilizer of gamma prime? Under this gamma action on the conjugacy class. Are people following me at all? You all know what a conjugacy class is, right? Right. So, C of gamma 1 is equal to the set of gamma 2 such that there exists a gamma prime with gamma prime, gamma 2, or let's say gamma naught. Gamma naught, gamma 2, gamma naught inverse equals gamma 1. That's the definition of a conjugacy class, right? Now, I claim that gamma acts on C of gamma 1. How does it do it? Well, it takes gamma 2. If I take a gamma in here, it takes gamma 2 to gamma, gamma 2, gamma inverse. Obviously, this maps the conjugacy class to itself. Equally obviously, it's transitive. Any 2 points in the conjugacy are related by such an action, right? Now, what's the stabilizer? Choose a point, gamma 1. What's the stabilizer? The isotropy group of gamma 1. It's some subgroup of gamma which fixes
the conjugacy class of gamma 1.
No. No, there's a subgroup of gamma. So what does it mean to be a stabilizer? Gamma is in the stabilizer of gamma 1 if gamma, gamma 1, gamma inverse is gamma 1. That's what it means to be in the stabilizer under the conjugation action. What is that group?
Gamma 1, gamma itself.
It is in. Gamma 1 certainly will sit inside that group. That's true. it is true that gamma 1 is in the stabilizer group of gamma 1. That is a true statement. So is the identity. If I take the identity times gamma 1 times the identity inverse, I also get gamma 1.
The elements that can use everything?
Pardon?
The elements that can use everything?
Perfect. The stabilizer of gamma 1 is equal to the centralizer of gamma 1. Now, by the orbit theorem, that means that C of gamma 1 is isomorphic to gamma mod Z of gamma 1. There's a transitive group action. It's a homogeneous space. So we've got finite groups here. So the order of this is the order of this divided by the order of that. Rewriting this equation, C of gamma 1, the order of C of gamma 1 times the order of the centralizer of gamma 1 is gamma, independent of gamma 1. Well, well, well. What did we see here? C of gamma 1 times the order of the centralizer, independent of gamma 1. So it's just the order of the group gamma, and I can pull it out of the sum. Yes?
For the shifting to the compact non-finite group case,
Yeah.
What subtleties would emerge when you're making this this argument? We're taking the order of each of the subgroups.
Well, no. Then we're dealing with infinite groups,
Right.
and we're not going to talk about orders.
Right.
But we can talk about volume elements, and factor. And if you do gauge fixing properly, you will take into account how volume elements change. That's called the Faddeev-Popov determinant. So in a sense, this is a sort of very baby version of the Faddeev-Popov determinant. All right. So we have done this check. Now let's relish some of what we've achieved. Let's solve Yang-Mills theory in 1 plus 1 dimensions, at least for a finite group. We're all set up to do it. Now, you see, as I said, a bundle comes with a canonical connection, so the action can't be an interesting function. In fact, remember that our holonomy was only dependent on the homotopy of a path. That means it was a flat connection. Now, most of you know that a flat connection has a zero field strength, so the Yang-Mills action is just zero. Okay? So it's clearly a topological field theory. Okay? There are no local degrees of freedom. But it's still a little bit interesting. So we have 1 plus 1 dimensional Yang-Mills for a finite group gamma. So what's the Hilbert space? So what's H gauged on S1? Well, you see, we get back to that group point. We have wave functions on the set of principal bundles with connection. So we have a psi of P of gamma, and it must satisfy the Gauss law. So we might as well write psi of P of gamma as psi of gamma. And then the Gauss law means that psi of gamma is a class function. Okay? Psi of gamma is equal to psi of gamma naught inverse. So the Hilbert space is, let's write it this way, L2 of gamma. Now L2 is a little overdoing it a little, right? Because it's a finite group, but it's still a true statement. So it's the set of class functions on gamma. Complex valued class functions on gamma. Now, what about, now I said it's a topological field theory. And if you think way back to the beginning of the course, I showed you how basically all we need to know is the Hilbert space and the amplitude for three-hole spheres. Okay, so how are we going to calculate that? So supposing I have a three-hole sphere that I write this way, and let me choose some bundles so I can, some base points so I can trivialize my bundle. And supposing I have P of G1 here, ingoing, P of G2 here, ingoing, and then I can choose my trivializations so that the parallel transport is just 1 along these dashed lines. And so therefore, the holonomy as I go out around the outer circle, the outgoing circle, is G1, G2. And so the holonomy is G1, G2. So I'm saying that if you want to put principal bundles with holonomy G1 and G2 on the inner circles, then on the outer circle, your principal bundle has to be one with holonomy G1, G2. Okay. So that means that if I have some ingoing wave function, psi1 and psi2, then the outgoing wave function is psi1 star psi2 of h is equal to the sum over h equals G1, G2 of psi1 of G1, psi2 of G2. So we have a Frobenius algebra here, where we have class functions on the group. We have class functions on the group, and the multiplication law on that class function is the convolution product. Does that ring any bells? Think back to our discussion of topological field theories. Remember, I showed you what a topological field theory is. I showed you how you could solve it completely given the data of a commutative Frobenius algebra in 2 dimensions. And I gave you some examples of what are called semi-simple topological field theories, semi-simple Frobenius algebras. And my first example was the class functions on a finite group with the convolution product. So you might all be very sleepy and tired and burned out in the middle of the second half of the semester. But it is true that you have seen this topological field theory before. Okay? And not only that, we solve for the partition function by gluing. And you have notes, so you can go back and see. And so we can deduce right away that the partition function on a genus G surface, okay, let's call it a genus P surface, not to confuse G with a group element, is the sum over R in the irreducible representations of gamma over the dimension of R to the 2p minus 2. And I wrote that formula. I wrote this side of the equation way back then, and I asked you if you had any sense of what that elegant formula is counting. So I asked you at the time, what we solved for this. This was the result we had, and I asked you, what do you think this is counting? Now you really know the answer. This is counting principal gamma bundles weighted by automorphisms on a genus G surface, genus P surface. Okay? I think it's a very beautiful formula. So this is the formula for the Yang-Mills partition function on a genus P surface. Let's check it. Okay? Let's check it to make sure that we haven't made some mistakes. So let's look at Z Yang-Mills on genus 0, S2. Okay? So what happens here? So P is 0. So we have 1 over gamma squared of the sum over the irreducible reps of gamma of the dimension of R squared. Now, it's a beautiful result from finite group theory that if you sum the squares of the dimensions of the irreducible representations of a group, you get the order of the group. Those of you who have taken my course on group theory should know that. So this is equal to gamma divided by gamma squared, also known as 1 over gamma. Well, what are the principal gamma bundles on the sphere? Do you remember how to classify principal gamma bundles for a discrete group? Remember, it's the homomorphisms. It's classified by the monodromy representation. Remember, it's homomorphisms of pi 1 into gamma modulo conjugacy. Do you remember pi 1 of the sphere? Pi 1 of the 2 sphere is? Z. Pi 1 of the 2 sphere, let me try again. Pi 1 of the 2 sphere. 0. You can't lasso a basketball. Right? Okay. So, how many principal gamma bundles are there on the 2 sphere? Just the trivial one. Now we said, what are the automorphisms of the trivial bundle? X times gamma. The automorphisms is just gamma. Well, this is perfect. So this is 1 over the automorphism group of S2 times gamma. Just like it should be. Okay? Let's check one other thing. Let's check it on the torus. So let's look at Z Yang-Mills of the 2 torus. So what's that? That's the sum over R in the irreducible representations of gamma of what? Anybody? Torus is genus 1.
Could you repeat the question?
We're checking this result, our main result here, for the partition function of Yang-Mills on a genus P surface for the case of a torus. So what is P? P is 1. So what is the sum here? 1. Okay. So this is equal to the number of irreducible representations. But another thing, those of you who have taken a course on group theory will know, is that that's the same as the number of conjugacy classes. Which is equal to the sum over the automorphisms. Is equal to the dimension of our Hilbert space. Okay, so that works. See, the Hilbert space is the space of class functions. So the dimension of the space of class functions is the number of conjugacy classes. Because a class function is determined by its value on a conjugacy class. So there's a basis of class functions, namely the one which is a delta function for each conjugacy class. Okay. So this is manifestly the same as the dimension here. Okay. Now, coming back to this, let me make one remark. One rather surprising aspect of this formula here, is that it doesn't actually remember the gauge group, gamma. So we can have let's Z Yang-Mills on sigma p gamma equals Z Yang-Mills of sigma p gamma prime for 2 different gauge groups gamma and gamma prime. Seems a little surprising. So the theory has forgotten a little bit what the underlying gauge symmetry is. What's an example? Well, take gamma to be an abelian group. Okay? If you have a finite abelian group, all its irreducible representations are one-dimensional. And the conjugacy classes is the same as the group itself, right? Because it's abelian. So what you have here only depends on the order of the abelian group. So for example here, if gamma and gamma prime are abelian, Z n mils of sigma p gamma only depends on the order of gamma. But as I hope you all know, two abelian groups of the same order need not be isomorphic. Anyone want to suggest an example? Two abelian groups which have the same order and are non-isomorphic? Come on, those of you who have taken my group theory course.
Z4 and Z2 cross Z2.
Right. Right. Z4 and Z2 times Z2, the simplest example. One has an element of order 4. The other obviously only has elements of order 2. All right. So, you know, this is a very baby example, obviously, but this is a big deal in more complicated gauge theories, like supersymmetric gauge theories, where there are all sorts of dualities, where the same physics is obtained by looking at very different gauge groups. So, for example, there's a very famous example in n equals 1 super Yang-Mills, super QCD, due to Zyberg, where we take SUNC gauge theory with NF fundamentals. Okay, and then for an appropriate range of NF and NC, Zyberg argues that this is isomorphic to an SU NF minus NC gauge theory. So Zyberg is very fond of saying that only global symmetries are things you can trust in the infrared. Gauge symmetries, you can have different gauge groups which are not isomorphic, which are completely different, and yet lead to the same observable physics. And this is a very trivial example, but still, I think, an illuminating one of that phenomenon. Now, although we have not officially talked about connections, I can't resist telling you about the generalization of this to any compact gauge group. So there's some things about what I'm about to say that I can't expect you to understand everything, but you'll probably get something out of it. So let me tell you how this story generalizes to an arbitrary compact group. Now it can be a continuous group, an infinite order group like SU2. Okay? And the solution, in fact, was worked out a long time ago by Migdal. And it's quite beautiful. So, again, there are no local degrees of freedom. But the theory is not quite topological. It's almost topological. The theory has no local degrees of freedom, but depends on the metric only through the area, as we'll see. So in other words, in our geometric category, we would have to talk about surfaces with an area. That's all we need to give it. And ingoing and outgoing circles with a length. All right, so the main fact is that the groupoid of G bundles with connection on a circle is again G mod G, with G acting on itself by conjugation. And the basic idea is the same. If you know what holonomy is in general, if you have a connection, you have a holonomy, okay? And that holonomy completely fixed. That's the only gauge invariant thing you can write. So I'm sure most of you have some idea of what a connection is. So that is the holonomy, and that's going to be our G. And of course, depending on where you put the base point, you know, that's only defined up to conjugation. If you change the base point, or you change the trivialization. If you don't understand that, we're going to discuss that in detail later. But anyway, having said that, you can understand that H gauged of the circle is again going to be L2 of G, G invariant, where G is acting by conjugation, which is equal to L2 normalizable class functions. Now the normalization is a more serious thing. We have a Haar measure on the group, and so our Hilbert space inner product is the integral dg of psi 1 of g star, psi 2 of g. Where I'm using a Haar measure, a left and right invariant Haar measure, invariant, normalized to volume 1. So that defines a Hilbert space. And now if G is compact, okay? So if it's not finite, then this Hilbert space is infinite dimensional. In fact, what is it? The beautiful Petter-Weil theorem tells me that L2G is the direct sum over the irreducible representations of G of R dual tensor R. Harmonic analysis on a compact group. And an orthonormal basis of class functions are the characters in these irreducible representations. Now, if we had discussed connections in a little bit more detail, then I could show you that the Hamiltonian of the Yang-Mills theory, acting on chi r, is e squared over 2 times the length of the circle times a function of the representation known as the quadratic Casimir. Again, I think probably most of you know something about that. If you take TA, where that's an orthonormal basis of your Lie algebra, then evaluate that on an irreducible representation, and you get a number, scalar operator, and that's C2 of R. Well, that's our Hamiltonian, so therefore we can say exactly what the cylinder propagator is. So we're now going to propagate for Euclidean time t, and so Z of t, G1, G2, is going to be the sum over the irreducible representations of the outgoing wave function, chi r of G1, times the complex conjugate of the ingoing wave function, chi r2 of G2 inverse, e to the minus e squared over 2, L t C2 over R. Okay? That follows from this formula for Hamiltonian. Now I said that this theory only depends on the area, and that's true. LT is the area. So you see we have L around here, T here, so the area of this is L times T. And let me simplify notation by defining a dimensionless area, capital A, not to be confused with connection, e squared over 2 times little a, and so I have e to Now, actually, another piece of the theory I skipped over before, but you can fill that step in, is you also need to know the cap, right? So how are we going to get the cap? Well, we're going to get the cap by gluing. So we're going to glue a cap of area which is 0 to the to an in or out circle on the propagator here. Now, how do we do gluing? So to do gluing, you need one more identity from group theory. You need that the integral on the Haar measure of chi r1 of hg, chi r2 of g inverse k is, first of all, a delta function on the irreducible representations. R1 and R2 are irreducible representations of chi r1 of hk divided by the dimension of R1. Okay, so that's what you need to know to do your gluing. Now, if we have a cap here of area A, then we get some outgoing wave function. Remember that? Whenever we have a boundary, okay, we have a cobordism from nothing to the circle, we get a state in the Hilbert space. And I claim that as A goes to 0, we should get a topological theory. Okay, and if you go back to this theory with a finite group as a motivation, then you'll see that psi of g is going to go to the delta function of g supported at 1. Okay, so a little bit of argument is needed there. Let's just proceed, just accept that. Then what we can do is we can find the amplitude for general area, A, from this formula for the propagator and this formula here by gluing in, if you like, a 0 area disk. And so then this becomes the sum over R of the dimension of R, chi R of G, e to the minus A, C2 of R. So you use this formula. And then we need to know the three-hole sphere. Okay? Okay, so you need another, how are you going to get the three-hole sphere? So you cut open the three-hole sphere. And so you make a 9-sided polygon. So how's it going to go? So we have holonomy G1 here, identification, identification. Let's say some other identification here, G3 here, identification, G2 here, whoops, no, wrong, identification, then aside with G2 here, and then identification. Okay, so if you glue this to this, you're going to get a hole here with holonomy G2. If you glue this to this, you're going to get a hole here with holonomy G1. If you glue this to this, then you're going to get a hole with holonomy G3. Okay? On the other hand, I just gave you a formula for the cap amplitude. So the amplitude for this whole thing, so you see, break this up into H, H inverse, K, K inverse, L, L inverse, okay? So your holonomy around the boundary of the disk is this complicated product of group elements. That's okay. That's what goes in here. This is for holonomy G around the circle. And now you just have to integrate out H, K, and L. So the identity that you need for that is this one, the integral dg of chi r of g, h, g inverse k is chi r of h, chi r of k divided by the dimension of r. Okay, so you do this gluing 3 times. Each time you get a 1 over the dimension of r. You're starting with a cap amplitude with 1 factor here. And so our result is that if we have holonomies G1, G2, and G3, then the amplitude Z for that is equal to the sum over R of chi R1, sorry, chi R of G1, chi R of G2, chi R of G3, divided by the dimension of R, e to the minus area C2 of R. Okay, now that we have the 3-held sphere and we have these gluing formulas, we can work out, we can just glue them all together to get the partition function for a Riemann surface of genus P. And what is it going to be? It's going to be a sum over all the representations of 1 over the dimension of the representation to the 2p minus 2 e to the minus a c2 of r. Well, that's a really nice check on what we had over here for our finite group. We had a little renormalization. You see, the order of gamma, of course, would be infinite in this case. So, you know, there's always the freedom in how you normalize the dilaton in topological field theory. So you can always change in topological field theory by some overall power of the string coupling to the 2p minus 2. Okay, so there's always that ambiguity here. If you like, we fixed that ambiguity in this case by these 2 checks. One of them would have sufficed. Wrong. For the torus, of course, we don't get the string amplitude. We have to use this check to fix the string coupling. Okay, so but we've gotten this one, and this is correctly normalized. So that is the beautiful answer for the partition function of 1 plus 1 dimensional Yang-Mills theory for any compact group on a Riemann surface. And you can go on and write down amplitudes for surfaces with holes, with Wilson line amplitudes. You can really completely solve this theory. And let me end with one final remark about this theory, which is quite beautiful. So, since we have this exact solution, you can try and learn something about Yang-Mills theory by studying this, albeit Yang-Mills theory in 1 plus 1 dimensions. And in the mid-90s, David Gross and Lottie Taylor studied this for G equals SUN. Okay. Now, you see, already for SU2, this is an interesting function. You see, in SU2, the irreducible representations are labeled by their dimensions, right? There's one irreducible representation for each natural number. 1, 2, 3, it's the dimension of the representation. So notice that this is a zeta function. This is a generalization of the Riemann zeta function. Now, if you do SUN, then there are many more labels, right? For all these Dinkin labels for the representation. So it's not completely trivial. But they were clever, and they found some expansion of this at large n. And found the 1 over n asymptotics. And now suppressing some technicalities, which you can look in the references in the notes if you're interested. At area A equals 0, it is roughly speaking a holomorphic square of what you might call the chiral partition function. Of course, if A is equal 0, we'd better put the genus bigger than 1, convergence. And the z plus turns out to look like 1 plus the sum from n equals 1 to infinity of 1 over capital N to the 2p minus 2 times little n, and then a sum over group elements, S1, T1 through Sn, Tn, sitting inside the symmetric group on n letters, of 1 over n factorial of the delta function of the product from j equals 1 to p of Sj, Tj, Sj inverse, Tj inverse. Now that's the delta function supported at 1 on this final group, plus some other contributions, which I'm suppressing. But I wrote this out to see if you've learned anything. Does this suggest anything to you? So what would it mean for this delta function to be saturated? It would mean you have this thing equals 1. Does this remind you of anything? Yeah.
The fundamental group presentation of the fundamental group of the torus.
Go ahead. Torus.
Oh, sorry. If all the j's are just 1 and we just have alpha.
I think what you're trying to remember is that if I take the fundamental group of a genus P surface, then it's generated by alpha j and beta j, such that the product of the group commutators, 1 to p, of alpha j to beta j, equal to 1, right? That's the fundamental group of a Riemann surface of genus P. So what would it mean if I can find elements of the symmetric group such that this product is 1?
Are we factorizing some Riemann surface into?
No. So if I can find Sj and Tj such that the product of Sj, Tj from j equals 1 to p is equal to 1, then I have found a homomorphism. It's called chi from pi 1 of a Riemann surface of genus P into Sn. Right? Because pi 1 is generated by generators alpha and beta with one relation. The product of the group commutators is 1. So in order to define a homomorphism into, say, the symmetric group, all I need to do is find symmetric group elements such that that relation is satisfied. Then I take, what is my homomorphism? My homomorphism takes alpha j to Sj and beta j to Tj. Right? The alphas and the betas generate the group. So if I tell you what the generators do, I know what every group element does, but I have to check that the relation is satisfied. So, out of the blue, Yang-Mills theory for SUN, out of the blue comes this, Riemann surfaces. Totally out of the blue. Nobody asked for them. Nobody put it in. You see? It came out of the 1 over n asymptotics. Now, that's weird. And there's something else that's going on here. What is... You might have said that I was getting too enthusiastic. Probably you should have said that. I mean, after all, I'm studying Yang-Mills theory on a Riemann surface. But I'm excited about something else here. So what does the homomorphism from pi 1 into Sn give me? morphisms of pi 1 of sigma p into gamma, mod gamma is equal to the principal gamma bundles over sigma p. Now for the symmetric group, so we're saying we have a principal symmetric group bundle over sigma p, and that's another Riemann surface. And so we're looking, what we're doing here is we're summing over maps of an n-fold cover over sigma p. This is, here is a sum over maps of covering Riemann surfaces. So what have I said? What have I just told you? I just told you that 1 plus 1-dimensional Yang-Mills theory in the large n limit is a string theory. We have a sum over Riemann surfaces mapping into the space-time, which is sigma p. Okay? And what is this 1 over n? This is, what does this relate to? This is the Euler character of covering Riemann surface. So this identifies the string coupling with 1 over n, just like it should. All right. That concludes our discussions of Yang-Mills with a discrete group. And next time, we're going to talk about something entirely new. We're going to talk about the stable homotopy groups of the Lie groups. What are the homotopy groups of the Lie groups? And while I'm making announcements, on Monday, November 15th, no class. I'll remind you again on Wednesday. All right.